For decades, the U.S. Navy operated on one assumption: no adversary could track a carrier strike group continuously from orbit. China may have just ended that era. A radar satellite parked 36,000 kilometers above Earth reportedly locked onto a moving ship, imaging through clouds and darkness, and never let go. NASA has stayed quiet, and the technology making this possible is what no one is discussing publicly. Synthetic aperture radar, SAR, operates on a principle that sets it apart from the cameras and telescopes most people imagine when they think of satellites. Instead of capturing sunlight reflected from the Earth, SAR systems send out pulses of microwave energy and record the faint echoes that bounce back. This active approach means SAR is not limited by daylight or clear skies. Rain, smoke, fog, and darkness have little effect. The real breakthrough, though, comes from how SAR uses motion. As the satellite moves along its orbit, it continuously transmits radar pulses. Each return signal is slightly different, depending on the satellite's position. By combining thousands of these echoes using sophisticated signal processing, SAR builds up a virtual antenna much larger than anything that could actually fit on a rocket. This synthetic aperture is what allows for sharp, detailed images, sometimes down to a meter or less, despite the physical antenna being only a few meters wide. The process hinges on two core factors: range resolution, determined by the width of the radar pulse, and azimuth resolution, shaped by the satellite's motion and the coherence of the signal processing. The wider the bandwidth, the finer the range detail. The longer the synthetic aperture, the sharper the image along the satellite's path. Unlike optical satellites, which are blinded by clouds or night, SAR can revisit the same area under any conditions, producing consistent, reliable imagery. This weather independence is not a side benefit. It is the main reason militaries and intelligence agencies have invested heavily in SAR for decades. With the right algorithms, SAR can even detect subtle changes over time, such as the movement of ships or vehicles, shifts in terrain, or the construction of new facilities. The ability to form a detailed picture regardless of the weather or time of day is what makes SAR a strategic asset in surveillance and reconnaissance. The next question is how far these capabilities can be pushed and what changes when a satellite can maintain an unblinking radar stare from high above the same region, hour after hour. L-band synthetic aperture radar operates at wavelengths around 15 centimeters, a range that behaves differently from the higher frequency bands often used for fine detail imaging. This longer wavelength gives L-band radar a unique advantage: the ability to penetrate dense vegetation, dry soil, and even shallow water. In practice, L-band signals can reach up to 30 centimeters beneath the surface, revealing objects or disturbances that would be invisible to optical or higher frequency radar. For military planners, this means camouflaged equipment, hidden supply routes, or shallowly buried infrastructure become much harder to conceal if they lie within the radar's reach. The power of L-band SAR is not limited to what lies just below the surface. When satellites collect repeated radar images of the same area, interferometric synthetic aperture radar called INSAR can detect changes in the ground's position with astonishing sensitivity. By comparing the phase of radar waves from different passes, INSAR can spot deformations as small as a few millimeters. This technique has been used worldwide to monitor landslides and earthquakes, but in a security context, it can reveal subtle ground shifts caused by tunneling, underground construction, or the movement of heavy vehicles beneath tree cover. The European Space Agency's ALOS 2 L-band satellite, for example, has demonstrated deformation measurements accurate to about 3 millimeters. The practical impact is clear. L-band SAR and INSAR together offer a toolkit for tracking not only what is visible on the surface, but also what is concealed below vegetation or shallow soil, and how the ground itself changes over time. These capabilities expand the reach of surveillance far beyond what traditional satellite imagery can provide, challenging long-standing assumptions about what can remain hidden from space. As China integrates these techniques into persistent, high-altitude surveillance platforms, the line between what is observable and what is secret has grown far thinner. China's official announcements around LSAR 401 describe a capability that, until recently, existed only as a theoretical possibility. Launched into geosynchronous orbit 36,000 kilometers above the equator, this satellite is billed as the first of its kind, a synthetic aperture radar, or SAR, able to maintain a continuous watch over a vast region of the globe. Unlike the fleeting glimpses offered by low Earth orbit satellites, LSAR 401 promises a constant, unblinking radar stare day and night in all weather. Chinese media and technical briefings highlight several headline features. The satellite's L-band radar operates at wavelengths around 23 centimeters, allowing it to see through clouds, smoke, and even dense vegetation. The public specifications claim a ground resolution as fine as 1 meter, a figure that, if achieved, would represent a leap in geostationary radar imaging. The antenna itself is described as a deployable structure several meters across, with phased array technology enabling electronic beam steering across its enormous footprint. From its fixed position above the equator, LSAR 401 can reportedly track moving targets, detect changes in the landscape, and provide millimeter-scale deformation measurements using interferometric techniques. The idea of continuous coverage is central to the program's messaging. In contrast to the brief windows of observation typical for low-orbit satellites, a geosynchronous SAR can monitor the same area for hours or even days without interruption. This persistent presence has clear implications for military surveillance, disaster response, and maritime domain awareness. Official statements point to the satellite's ability to follow ships across open water, monitor large-scale infrastructure, and even detect underground facilities or submarine wakes, capabilities that, if realized, would reshape the strategic balance in space-based intelligence. Hardware details remain limited in public sources, but the core claims are clear. LSAR 401 is positioned as a technological breakthrough, offering a combination of wide area, all-weather, and continuous radar imaging from a single platform. The promise of 1 meter resolution, a few meter class antenna, and uninterrupted regional coverage sets a new benchmark in the field. Whether these specifications are fully achievable with the disclosed hardware is a question that invites closer scrutiny. At geosynchronous altitude, the numbers tell a different story than the headlines. The radar equation lays out the challenge: free space path loss at 36,000 kilometers reaches about 147 decibels, an immense drop in signal strength before any echo returns to the satellite. To offset this, engineers turn to the antenna resolution formula. For L-band, achieving true 1 meter ground detail from geosynchronous orbit would require a physical or synthetic aperture of at least 50 meters across, far exceeding the size of any currently deployed space structure. The actual LSAR 401 antenna, as disclosed in technical briefings, measures around 12 meters. That size, combined with a few kilowatts of transmitted power and a 200 megahertz bandwidth, supports a best-case resolution of 20 to 25 meters. This lines up with what independent analysts have confirmed from released imagery, such as the Toamaru demonstration, where the pixel size hovered around 25 meters and the positioning error was about 3 kilometers. Even with advanced signal processing and long integration times, the physical limits remain. The power budget for sub-meter imaging from geosynchronous orbit would require tens of kilowatts, well beyond the capacity of current solar arrays and thermal management systems on Chinese platforms. The 3-satellite global coverage model, often cited in public briefings, is geometrically plausible for persistence in wide area monitoring. Each geosynchronous satellite can view a swath nearly 12,000 kilometers wide, but coverage thins out near the poles. Regions above 70 degrees latitude fall into a persistent gap outside the reach of the beam. The promise of continuous high-resolution imagery everywhere on Earth is more ambition than reality with present-day hardware. Peer-reviewed engineering studies and patent filings reinforce these boundaries. No nation has yet demonstrated operational geosynchronous synthetic aperture radar with sub-kilometer resolution. The most credible open-source assessments agree. China's LSAR 401 is a breakthrough in persistence, not in fine detail. The claims of seeing through walls or tracking every target at 1 meter precision from geosynchronous orbit remain aspirational, shaped as much by strategic messaging as by physics. The real test is not in the laboratory, but in the operational consequences that follow. Carrier strike groups, once shielded by weather and darkness, now face a new level of exposure in contested waters. Haishao 1, operating from a very low Earth orbit, delivers up to 5.7 passes per day over the South China Sea. With its X-band radar and sub-meter resolution, it can track vessel movements and even detect the faint wakes left by ships or submarines operating near the surface. The signal-to-noise ratio is high enough for reliable detection in all but the roughest seas. When paired with the Yaogan constellation's fusion of radar and electronic intelligence, these satellites can cross-reference radar signatures with intercepted emissions, reducing the window for error and compressing the time between detection and action. For U.S. naval planners, this means the traditional margin for maneuver, once measured in hours or days, shrinks to minutes. The risk is no longer theoretical. With persistent, AI-assisted surveillance, the odds of slipping through undetected are lower than ever. PSAT's NUA constellation stands at the center of China's commercial SAR ambitions, with 114 satellites planned for launch between 2025 and 2032. This fleet aims to deliver hourly revisit times and meter-class imagery, backed by a $250 million Series B financing round in partnerships with major satellite manufacturers. The scale of this commercial push is reinforced by a 38% surge in Chinese SAR-related patent families since 2022, now totaling around 320, many focused on AI-driven analytics and phased array antennas. As NUA moves toward operational status, the United States faces a clear set of choices, including accelerating geosynchronous orbit synthetic aperture radar prototype development, expanding commercial partnerships for rapid tasking, coordinating internationally on L-band spectrum, and monitoring patent trends to anticipate the next leap. The commercial scaling of SAR is no longer just a business story. It is a strategic transformation with real consequences for intelligence, deterrence, and global transparency. Continuous orbital radar coverage is no longer theoretical. It is operational, and the strategic calculus is shifting. As China publicizes synthetic aperture radar breakthroughs and the U.S. stays silent, every nation now faces a new reality. Secrecy is eroding at 36,000 kilometers. The era of hiding may be ending. What comes next?